To define our first trig functions, we need to start with a definition. We're going to say a point P on the edge of a unit circle has coordinates x, y. That's not really surprising because any point in the plane we can describe with coordinates x and y, but let's just draw in a little example here. Let's put a point right here. Let's call it point P. I'm going to draw a radius to that point. And then the angle, the reference angle that this makes with the positive x-axis, I'm going to call angle theta, which again is positive if I'm going in a counterclockwise direction. So what I'm going to do from there is I'm going to define, for a point P on a unit circle that makes angle theta counterclockwise from the positive x-axis, say sine of theta equals y and cosine theta equals x. So in this example here, I have angle theta and I have point P. Now point P in this case has coordinates. These are the approximate coordinates. I don't think this works out exactly, but P is about equal to an x coordinate of 0.9, a y coordinate of 0.4. So in this case, I would say that for this angle here and this point P, the sine of theta is about equal to 0.4. The cosine of theta is about equal to 0.9. That is, the y coordinate is sine, the x coordinate is x. So that's going to be one of the most important things to remember this term is think about on a unit circle, the sine is y, the cosine is x. It's always important to think about cosine as a counterclockwise revolution, but it could also be a clockwise revolution. You just have to keep in mind that theta would be negative. This is going to work the same way. This is a very nice way to look at trig functions and angles, because any value of theta you put in here, whether it's whatever degrees I have here, something around 15 or 20, that's going to work out. If theta is negative, it works out. I could go 90 degrees for theta. It looks something like this. Let's call this theta 2. Where if I go theta 2, I extend a radius out this way, I end up at this point. This I'll call point P2, which has coordinates 0, 1. So then I go up here and I say the sine of theta 2 equals the y coordinate, which is 1. The cosine of theta 2, which is the x coordinate, is 0. So this works for any point. Let's do something even more strange and go all the way around here and all the way around again and all the way around to here, and then let's draw in a radius this way. Now this angle, I've gone all the way around 360 degrees. I'll call this theta 3, and I've gone, theta 3 is going to be a 360 degree rotation because I went all the way around once from here to here. That's once. I went around another 180 and another 90, so plus another 270 plus another 45 degrees. So full rotation for 360, rotation, 3/4 rotation for 270, and another 45 here. That gives me a total of 675 degrees. So if I ask myself, what is the sine of theta 3? It's approximately equal to the cosine of theta 3 is approximately equal to. Well, I'm just going to read those off here. This is 0.5, 0.6, 0.7. Looks like it's just a touch over 0.7. Let's say 0.71. Here, negative 0.5, negative 0.6, negative 0.7. It looks like this is about negative 0.73 or so. So the sine is going to be the y coordinate. Remember, I can draw in this triangle here, and I can get the x coordinate is about 0.70 or maybe 0.71 actually, now that I look at that. Sine of theta 3 is going to be about negative 0.73. And so that's how the trig functions work. Whenever you're asked to find the sine or cosine of an angle, think about it as the y coordinate for sine, the x coordinate for cosine on a unit circle.